Fascinating. Today's the 15th, yeah. Okay, Ides of March. That's right. Beware, Caesar, the Ides of March. But I don't think you have much to worry about. So we talked about spring constants. You're good at mechanical energy. You can compute spring constants for an elastic material. You can do all that. So we've talked now about potential energy due to gravity, due to elasticity. We've talked about kinetic energy. These have something in common. They are all lumped in to one kind of energy that we call mechanical energy. So we're going to start off talking a little bit about the conservation of energy. So you have heard this, and if we went back to your what do you know, a lot of you said energy can never be created or destroyed. Energy can never be created or destroyed. That was a common thing that came up in your what do you know. You've heard that since, I don't know when, 6th grade, 7th grade, freshman year? You've heard that for a long time. We're going to put some qualifiers on that because it's mostly true. It's mostly true. The generality is we can switch forms. And you remember this from your freshman year. And the classic example is the roller coaster. At the top of the first hill, you have tons of what? Tons of gravitational potential energy, very little kinetic energy. As you drop down the hill, you build kinetic energy at the expense of potential energy. Then you have enough momentum that you've got kinetic energy, which carries you up the next hill, where again, your kinetic energy drops, but your potential energy rises. And you just keep doing this until it's all lost. Huh? What's the problem? Can't lose energy, Moser. Can't lose energy. What do you mean? If you couldn't lose energy, the roller coaster would just keep going. And the hills could all be as high as the first one. Right? If all we were doing was trading potential and gravitational energy, we have this number of joules of potential and, this number of joules of kinetic here, x plus y, and our total at every single point along here should still be x plus y, because we're just swapping forms. But you know that on a roller coaster, the hills get smaller as you go. You get less kinetic energy, which can lift you up that hill to get your gravitational potential, to get kinetic, to get gravitational potential, and it just keeps dropping off. So, we say that the energy in the system is conserved. This is what we say. This is what we claim. It changes forms. Can't be created or destroyed. It's the law. It's more than a good idea. It's the law. It's the law of conservation of energy. So, back to the roller coaster issue. Why doesn't the roller coaster go forever? Pardon? Outside of what? Okay. Frictional forces. Which are, they're internal to the system. They're between the car and the track and the metal and all that. But are we losing energy? So, let's now talk a little bit about this concept of mechanical energy. When we look at that roller coaster or anything else, if we add up at any moment, and I'll redraw my little roller coaster here, at any moment here, or here, or here, any place, we look at all the kinetic energy and all the potential energy, and we sum those, we call that mechanical energy. And mechanical energy excludes all forms of energy that are not at kinetic or potential. So the energy contained in the atom in the nucleus, nuclear energy, excluded. The energy contained in a liter of gasoline, the energy of chemical bonds, excluded. The energy of electrons moving, excluded. Any energy that is internal to a material, excluded. Okay? So we're just dealing here with kinetic and potential. And that potential can be potential elastic, potential gravitational. The kinetic is, well, we only have one kind of kinetic energy. We add those two things together, what we get is the mechanical energy. So, if this was a perfect world, we would not lose a single drop of mechanical energy. The mechanical energy you started with in the system would be the same mechanical energy you feel finished with. Initial would equal final. What happens, and we actually, were you ever told, like, when you say, well, energy is lost as heat? No, you can't say that. You don't lose energy. Did you ever have that come up in physical science? Okay. Here, we're going to say, yeah, it's lost. Because it's lost to a non-measurable form. So mechanical energy is lost. And non-mechanical energy is, in essence, gained. We're not actually losing energy, but we are losing mechanical energy. So in any system where we get a lot of heat generated, and this is typically systems where we see friction, we're going to talk about that next, we transfer mechanical energy to non-mechanical energy. And we can say, yeah, we lost mechanical energy. We have a loss of mechanical energy. Now, because we like to fudge things in high school level physics, you know, that imaginary frictionless surface that we keep using, we very often, as long as the amount of mechanical energy that is lost to friction is small, we just ignore it. And we pretend that there is a perfect conservation of mechanical energy. Okay. And so this is where we say, in any system where the friction is significant, then we do actually have to acknowledge that there is a loss of mechanical energy, and we can't use the conservation of mechanical energy to solve problems. We ignore friction when we can. We're going to do a whole bunch of problems where we completely pretend there is no friction. And there's friction from air, there's friction, I mean, air resistance is friction from air. You know, a car moving through, you know, moving at 65 miles down the road, 65 miles per hour, has got significant air resistance. But we're going to ignore it where we can. If we do have to acknowledge it, we do talk about it as a loss of mechanical energy. So, okay. We're going to do sample problem 5e together. Then I'll turn you loose to do practice problems together. We have a single period today, but I think you can get... Do we have a double period?
It's Tuesday.
Oh, it's Tuesday. Okay, so we have... Oh, I'm sorry. A double abbreviated period. So we have a kid coming down a frictionless, of course it's frictionless slide from 3 meters. What is her speed at the bottom of the slide? Assume that the child has a mass of 25 kilograms. So here's what we're going to use. Mechanical energy final is equal to mechanical energy initial. And what we have to think about for those is what goes into mechanical energy. Well, your mechanical energy final is going to be your potential energy due to gravity, final. In this case, we don't have any elastic potential energy, plus your kinetic energy, final. I'll scoot this over just a little bit. No, I'll put it down here because I can't do that. And what we're saying is that that's going to equal your initial potential gravity, or potential energy due to gravity, and your initial kinetic. Okay. So you have formulas for each of these. Potential energy gravitational final would be what? Mass times gravity times final height. You can put that in parentheses if you want. Final kinetic energy would be what? 1/2 mass velocity final squared. You can also do that if you want. And of course that and I'm going to cheat this because I'm using Doceri and I can. All the same stuff with your initial values put in. So that's not actually too bad. And what has happened year after year is, like I said, it's like in calculus, you do limits, 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 limits for, you know, how many weeks. And then they show you derivatives, first derivative. You're like, what? I could have just done that the whole way? This is kind of that beautiful shortcut where instead of doing all the work and the forces and doing the sum of forces and then finding the network and then finding the change in kinetic energy to find your, yeah. So we're told that the child is 3 meters. She has 3 meters to fall. So her initial height, her mass doesn't change, 25 kilograms. Gravity doesn't change, 9.81 meters per second squared. And her initial height is 3.0 meters. I'm desperately trying to plug that into the space that I have available, which is that. Okay. What's her initial kinetic energy? She's at rest at the top of a slide. What's the kinetic energy? 0. Okay, that's easy. That goes away. So we're treating the bottom of the slide as the arbitrary 0 for gravitational potential energy. She can't fall any lower than that. Now, in reality, yes, most slides have a little step between the slide and the ground, but we're ignoring that. So if her height at the end of the slide is our arbitrary 0, what's her potential gravitational energy at the end? 0. So now, and we want to know that final velocity. Well, we just made that really easy. Actually, I shouldn't have plugged in numbers here yet. We'll copy that down. There's what we've got. So we now have the final kinetic energy is equal to the initial gravitational potential. What we're saying is that there was no energy lost to heat. Okay, there was no friction on this slide. So if we want to solve for this, it's just algebra at this point. So 2 times mass, gravity, initial height, divided by her mass, so our masses cancel, square root thereof gives us our final velocity. Much simpler, I think. Much prettier. So now we can start plugging in values. We have a final velocity equal to the square root of 2 times 9.81 meters per second squared times 3 meters. You should have a raw value of 7.672027112 meters per second. If we sig fig, okay, book claims 3 sig figs. If you look back to the problem, I just put in, oh wait, the 3 meters. Yeah, they give it as 3.00 meters. So that was, I dropped a sig fig there. Yeah, the book gave that value as 3.00. So we would have 3 sig figs. So we would have 7.67 meters per second for a final velocity. These are so nice. They are so nice because here's what's generally happening. On one end of the problem, your potential energy is 0, and on the other end, your kinetic energy is 0. It's kind of lovely. So you're using this basically sum of mechanical energy, conservation of energy, to find one of those factors. Okay? So all of the practice on page 185 is assigned. So page 185, numbers 1 through 5. This is the 5E practice. And I'm going to give you this period to work on them. What I think we will do is we will have our conceptual conversations about power in the next period that we're together. So I'll give you the rest of this in about 10 more minutes. Then we'll have a brief conversation about power. We'll probably do a sample problem together. And that pretty much wraps it. So